Everyone, welcome to this new session on switching theory and logic design. Myself, Dr. Sohail Rana, and we are studying minimization of switching functions. This is our part 8 and session number is 40. In previous session, we have started examples on 4 variable K-map. In that we have seen one procedure and the example. So now let us continue our discussion and let us discuss few more examples on 4 variable K-map. So let us take next example. Say we will have example. This today's first example is reduce using mapping the expression f equal to summation of m 0, 1, 2, 3, 5, 7, 8, 9, 10, 12, 13 and implement the real minimal expression using universal logic. So here in this example we are given with one function. Now this expression in this expression we have 1, 2, 3, then 4 is missing, then we have 5, 6 is missing, then 7, 8, 9, 10, 11 is missing, then 12, 13, 14 and 15. So these functions we can say that in POS form this function is given as say capital M. So for max terms, remaining term we can write here. Say these remaining terms are 4, 6, 11, 14 and 15. So we can draw K-maps for POS as well as SOP form also. So their reduction and reduce expression we can obtain, and for that first we have to make the K-map for say POS and K-map for SOP, and we will reduce that, and after that we can decide which one is using less number of gate inputs. And later part it is asking us to use universal logic. So universal logic can be implemented by any of the universal gate. For example, NAND is a universal gate, so we can use NAND logic. So first stage is to find out the K-map. So let us take this K-map and first let us solve for the SOP. First we will draw SOP K-map for the SOPs. So this side is AB, this side we are representing CD. So here we will just focus on the SOP. So actually we have to find out the real minimal expression. So for that we have to find out both min terms and max terms. For max term, let us put the numbers for min terms. Say this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Now we have to mark the number. So say this is at 0 position. So here we will write 1. Then this is M1 position 1. Then 2. Then 3, 5, 7, 8 and 9, 10, 12 and 13. 12 and 13. Now let us see if what are the possible combinations. First let us check for the combination of 4s. So here we will highlight, we'll make boxes wherever there are 4 combination. So this one, say we can make a combination of 4, and this one we can make a combination of 4. Now 4 corners of also we have 1. So this one corner, say this one and this one. Now apart from this, do we have any isolated term here? No, no one is remaining. Right, so like this we can write. So with this we can get 3 expression. One for these all corner ones, one for all these corner ones, say 2 for this square, third for this square. So in SOP form, what we can write here is, say this F, minimum F, min, F min, min. So one we will get as, say, B bar, D bar plus AC bar. Now say B bar, D bar. B bar, D bar is for M10, 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 then M0, M2 and M8. Okay. Then AC bar is for, say, M12, M12, then 13, 8 and 9. For this what we will get? AC bar, because here A is same and here C bar is same, 0. So here we can write AC bar. Third one we will get for this box. For this box, in these both columns, D is common and in this A is common. So here we will get A bar, D. So now this is the minimum min terms. So we have solved for SOP. Now similar way we have to solve for the POS K-map. Now POS K-map will be for the remaining terms. Remaining terms, just now we have seen 4, then here 6, then 11, 14, 15. There in POS form we have to mark it with zeros. So let us have for the POS form. So here we will do now POS K-map will make. So for that we have function as capital Pi is capital M 4, 6, 11, 14, 15. So this one we will put we'll mark on this. So before that, let us put numbering here. This is 1 0 1 2 3 4 5 6 7 8 9 10 11. So this one we have to remember. Third line will not start here. So often we can do this mistake. So third one we have to mark on the last line. So this is a very common mistake we have to remember. So after 7, 8 will go here, 9, 10, 11. Then 12, 13, 14 and 15. Now for POS form we have to mark zeros. The first 0 at 4th position, then second 0 at 6th position, then next 0 at 11th position, then next 0 at 14th position, next 0 at 15th position. Now remaining work is to make the pairs. First we will see if we can make pairs of 4. There are no 4, nothing in the corner. So, but we can make the pairs of 2. So this one we can pair with this one, and 14 and 15 we can pair, and 11 and 15 we can pair. Now for this we have to write POS. POS means product of sum. So we'll write it in the form of sum. So say we'll get this function f is equal to, say first for M4 and M6, this is M4 and M6. For this, what are the commons we will see? Say we'll get A plus B bar and D. So here we'll get A plus B bar plus D. This is first function. Then next, say for M15 and M11, say these two. For these two we have A bar, and this side B is changing, so will not take this side. Will take both 1 1, that is C bar D bar. So it will be A bar plus C bar plus D bar into the third remaining combination. Third remaining combination is say 14 and 15. For 14 and 15, C bar is common, and for these two, there is single line 14 and 15. So 1 1 we have to take. So that will be A bar B bar, and here C bar. So into A bar plus B bar plus C bar. Now this is the function for POS, right? So we will compare both of them. This is for this one. On separate page, let us write down. Say for F min, one term we got as B bar D bar plus A bar C bar plus A bar D, and another one we got as A plus B bar plus D, then A bar plus C bar plus D bar into A bar plus B bar plus C bar. This is SOP form, this is POS form. Now out of these two, what we can say, which one is useful? Now if we see SOP, we require say total 9 gate inputs here. We require 9 gate input. Now if we see this one, how many we require? 3, 6, 9, 10, 11, 12. Here require 2 gate, 12 gate inputs. So to realize which one we will prefer, so the better one which we can use is the SOP, because it requires 9 gate input. So the economical SOP form is more economical to realize. So out of these two, we will go with SOP. Now for this SOP, we can implement the NAND logic, right? So this term we can say also write as say F min is equal to say B bar D bar whole bar into, we'll use De Morgan's theorem, then A C bar whole bar into A bar D whole bar and bar of all of them. Now what is our remaining task? Remaining task is to just to implement the circuit by using NAND logic. So for NAND logic, we require B bar D bar A bar A C bar, and third one we require as A bar D. So that diagram we will see here. So using universal gate, that is NAND we are using in this case. So we will implement, say we have 3 functions, so we require 3 AND gates. So we have to use NAND gate. So first 2 inputs we will write down there. So we have B bar and D bar. So this is the first NAND. Similarly, second NAND we can connect with the second input, say A C bar, and we have third NAND gate. For third NAND gate, and the inputs are say A bar C. Now all these 3 outputs from this NAND gate we have to give to the next NAND gate, say the 4th NAND gate. Here we get the final output F. So this one will attach here, this one we attach here, and this one will attach here. So these are like our 4 NAND gates. So this is universal gate realization using NAND gate. Now there is one more universal gate, that is say NOR gate. So NOR gate also we can use. When we use NOR gate, we have to connect the circuit using the NOR gate. So NOR gate symbol, if you recall, we have, it will be like OR gate followed by one bubble. So NOR gate is also one kind of universal gate. So in this way we can implement the realization of logic, and based on the gate count we can decide which SOP or POS we have to use. Now a few more examples we will see in the next session. Till then, have a good day. Thank you.